Hello everyone. Today I would like to give a presentation about applying additive manufacturing for materials design. So additive manufacturing has become a very popular processing technique. However, right now we still have limited understanding of process structure property relationship in many of the additive manufacturing processes. This directly causing the problem. We have limited choices of new alloys or customized alloy for additive manufacturing itself. Therefore, this is a driving force for us to study this work. And then we were thinking about how to accelerate the design of additive manufacturing. One of the methods that we tried is doing the high-throughput computation with machine learning. However, if you don't have enough data, the machine learning or the high-throughput computation would be quite limited. Therefore, we need to make sure that we have data acquisition method, which allow us to get a lot of information for the processing structure property at the same time. Usually, we need to tend to the high-throughput experiments. So for the high-throughput experiments, I first like to talk about the high-throughput processing experiment. For the processing method, traditionally, we have diffusion couple or diffusion multiple method. We also have the combinational methods like using the sputtering, doing the thin layer deposition with changing of the composition. And right now, we also have a lot of efforts made through the additive manufacturing. So these high throughput methods, as I already mentioned, can support the model validation, but also develop such a kind of experimental database. So for the high throughput experiments, if we're talking about the traditional way, people use the diffusion couple or diffusion multiple. This is a kind of very nice case study that people performed for the moly, iron, nickel with the Inconel. So for example, if you do have a kind of diffusion couple, then for the chip junction, you can actually measure the ternary system and understand how to construct the isothermal section for one ternary. But if you don't have such a method, then you have to prepare a lot of alloys, which is not a preferred way and very tedious to measure all of this phase information. So through the high throughput processing using the diffusion couple or multiple, people can further determine the microstructure property relations like this. They can use the measurement through EBST, EPMA to determine the phase stability. They can also do the micro machining, micron compression, or nano indentation to study the localized property and the relationship with the microstructure. So they can further study some of the functional properties as well. Another process is using the sputtering technique. So basically, you can deposit different layers of the film, and then you can also control the deposition of the film at different locations. Therefore, you have such a kind of composition variation or composition gradient spread the whole deposition film. And then you can use the XRD or some other type of methods. You can determine the phase stability and identify different phases. So that's another interesting method that we use very often nowadays. And then the third method that using the additive as a high throughput is really such a kind of popular concept right now. So for example, if you have such a kind of laser deposition system, sometimes we call DED, directed energy deposition. So basically you have several different spray nozzles for the powder, and then you can spray the powder according to the dedicated composition. And for example, like this work, people deposit a kind of matrix with different composition for this copper zirconium aluminum system. Try to study the amorphous formation of this ternary system. Therefore, after deposition, people can do XRD to identify which region of the alloy composition is more preferred to form the amorphous. Especially this is very useful for additive, because additive is such a kind of rapid cooling process. So the metallic glass is also requiring the rapid solidification. So this is a kind of ideal case which people would like to explore. Another case that people also tried a lot is using so-called graded alloy deposition, or sometimes we can call it functional gradient alloys. So this is a kind of DED application as well. Basically, you have substrate, you deposit one type of alloy, and in between, for example, look at this figure A, then you have a gradient composition zone. And then you can further deposit another single composition alloy. Therefore, you will form a kind of gradient between alloy 1 and alloy 2. And look at the right figure, then you can study the process property and microstructure change along this building direction. And therefore, you can fix the alloy concentration at certain layer thickness. This is the kind of way that people nowadays using more and more popular. For the fundamental side, you need to do quite a lot of study for these phase relations according to different change of the composition. Indeed, additive manufacturing itself also has a kind of requirement where the similar alloy deposition become very useful. And this is also another advantage of additive manufacturing. So this is also a good example for having the additive manufacturing performing the high throughput to design the processing or the new alloy composition for itself. So this is another example which is still similar as I described before, using that directed energy deposition, but then people can just change the composition at different places. And further on, people can do the diffraction pattern and the microstructure analysis. This work is actually dedicated for understanding the reaction after irradiation and identify which complex concentrated alloy is more preferred to serve under irradiation. But another thing that we have to take care of is not only for the additive manufacturing itself, because all of this method that I described for the additive manufacturing part is actually focusing on the additive manufacturing as built alloys. Sometimes people can do post-heat treatment, of course, but then once you run the post-heat treatment, then this developed gradient composition zone will be start to diffuse. That's another challenge of utilizing the additive manufacturing. How about doing something else using the additive manufacturing? So this is kind of question that we were thinking about. And one of the driving force that we think about this is because we find a lot of complexity in the post-heat treated example by additive manufacturing. So this is kind of study that we performed with Inconel 718. As you can see, this is the figure showing the IPF on the EBSD. For additive manufacturing example, it shows a significant difference compared with the suction cast. This is as fabricated alloy. This is after 20 minutes, 1 hour, and 12 hours under 1200 degrees C. As you can see from this right figure, the average grain size for additive manufacturing examples, they actually even slightly decrease after 12 hours heat treatment. But then for the suction cast alloy, the grain size increases as we expected. So what's the reason behind? Is because in the additive manufacturing example, it has different distribution of the residual stress. And then this residual stress start to play a critical role once you hit the example at 1200 degrees C, which is above the recrystallization temperature. So this is a good thing, of course. We use the additive manufacturing pre-alloy, and then later on we don't need to worry too much about the grain refinement. But then, can we identify such a kind of optimum homogenization process? So this is another thing that we also see from the steel. We studied HSLA steel, high strength low alloy steel. And then for the additive manufacturing alloy and cast alloy, we find the maximum strength developed with additive manufacturing is actually at 80 minutes, while for the cast alloy, you can see the strength level at 60 minutes. So this is applied again for the homogenization. So we want to make sure that the grain size is not causing in very much. And sometimes we want to make sure that we find the optimum strength once we do the heat treatment or post-heat treatment for additive manufacturing samples. So if you checking about microstructure, you can see the difference as well between the casting alloy and the additive manufacturing alloy. And actually the grain size again for the additive manufacturing one behaved quite differently with the casting alloy. So that means we need a different post-heat treatment schedule for the additive manufacturing sample, even though the composition of this alloy is probably still the same as the traditional casting or welding alloy. So two questions now coming out. One is we have to design specific heat treatment for alloys made by additive manufacturing. And how can we accelerate the design? If you're running with the additive manufacturing process with something called, well-known steels or well-known alloy, how can we guarantee that we get the same property, similar microstructure, and then apply this alloy? So can we do it faster? So this is the efforts that we tried. So what we were thinking about is using the gradient furnace, we can establish such a kind of gradient temperature zone. And I have to say, this is not kind of a very unique heat treatment. So actually, there are a few studies already applied with traditional material. And people just do a casting bar with a long bar shape and then put it into the gradient furnace. But then what we think is additive manufacturing can actually do it better. So we can actually do additive manufacturing sample build with powder bed fusion process. And we did this with laser powder bed fusion and design two arrays of the holes. And then in these holes, we insert the thermocouple. And then put in the sample and thermocouple together into this gradient zone furnace. So this gradient temperature will allow us to heat treat the sample at different temperature simultaneously. Now, of course, according to your need, you probably don't need to insert all the thermocouple into every location that you designed before. But of course, you can pick up some of the critical temperature region that you are interested about. This is such a kind of demonstration, of course. And then we choose from 825 degrees C to 600 degrees C. And certainly, for this purpose, we just want to demonstrate the method. We want to validate if the method is feasible or not. So there are no surprise to us, because behind this work, we already did a lot of work for additive manufacturing of 718, including the post-heat treatment. We know the best temperature for strengthening precipitation happen even in this additive manufacturing 718 is still around 718 degrees C. So let's check the microstructure. And microstructure is not something that surprises us to a lot, because it's exactly the same as we were thinking about. And so we did the microstructure checking. We find at high temperature you have the delta phase, and coexisting with gamma double prime. At 716, you do have the precipitation of gamma double prime as the major strengthening phase. And of course, you can check the grain size as well, and you can also validate the strength through the hardness. And ideally, if you are dealing with a new type of material, you don't know anything, then probably this method will be very helpful. After you do a kind of heat treatment, and then you can actually do the aging process at this temperature, and further building a long bar shape with a tensor bar and test to verify this high throughput study. So, as I already mentioned, we were talking about processing method considered as a high throughput. For experiments, we have a lot of things to deal with, not only for the process, but also has the microstructure analysis and property measurement. So this is kind of an overview of the popular ones that I can find from the literature. And certainly I probably still missed some of the high throughput experimental technique. Here, as a final section, I would like to just review some of the microstructure analysis and the property test. The reason is because if you only have the processing as a high throughput, then here sometimes people would argue if this is a true high throughput, because you can get a lot of alloys, but then how to do a quick analysis of the microstructure property. So this is a kind of study people already did with optical serial sectioning. So you do have one sample prepared with optical, and then once you polish one layer, and then you check the microstructure. After you finish that, and then you grind and polish another layer, and then you check a layer furthermore with the depths going on. And then finally you get all the images stacking together at different layers, different height, and then you can reconstruct. So this is kind of example for the 3D reconstruction of the silicon carbide in the material. And of course, you can also do the SEM. For SEM, you can check with the FIB process. The FIB can actually do the series section, which is similar as the one that I showed before. However, the difference is for the SEM, of course, the length scale will be a little bit more refined. And I have to say this is pretty useful once you do some of the measurements for the additive manufacturing of the porosity distribution, because some localized porosity will be different even if you measure the overall porosity of the sample. And then some people also tested with a serial sectioning with EBSD measurement and microstructure analysis. Eventually you can also do such a kind of APS synchrotron. And a lot of people actually also did with the thin film deposition with the processing and synthesize this material with different concentration and to do the measurement. So these are the two examples I listed here for your reference. And for the hardness is a common way to measure for the properties, right? And certainly this is not sufficient enough to understand the elongation and toughness. However, at least you can get such a kind of sense in the beginning, helping you to narrow down the processing on composition range. This is the example people use the nano indentation working on the thermal barrier coating. And here is another example that people did with creep testing. So it's also similar to the indentation method. So you actually bend the sample at a high temperature, and then you can actually develop such a kind of measurement through the DIC. And finally, you can construct some of the parameters to understand the creep performance of the material. So this is a kind of tensor testing. I find this is also very interesting work because the people who worked on this is actually using the 3D printing to print series of mini scale tensor bar. And then they pull the tensor bar in an array like this, and then they can evaluate the strength of the material. That's a kind of fantastic in the future if we can really have such a kind of setup utilized for designing the additive manufacturing samples. I would like to say we still have something to consider once we utilize all of this high throughput method, because for a lot of high throughput method, for example, like even the traditional one, we need to consider the phase stability and phase transformations, because you need to ensure some phases they are not necessarily stable and then you have to making sure that the processing is long enough if you really want to study the stable phase. And kinetics would be becoming an issue sometimes. Like, for example, sigma phase is critical in the tube alloy, but the formation would be sluggish. And then the impact of the processing steps sometimes also very important, because if you do the aging, and then how much of the heat treatment you have to do before the aging step, of, for example, like homogenization, how such a kind of processing steps influence the next one that you apply with high throughput experiment. That's also critical in some of the kind of the design optimization if you want to utilize this way. And oxidation could be an issue even for the example that I just showed you with our work, because this tube alloy sometimes is fine, but if you really have easy oxidized material, then you have to consider run it probably in the glove box. And very important thing that I have to mention for the property and microstructure, especially for the properties that I showed you, is not necessary to be the standard way to measure. Therefore, it would be nice to have such a kind of standard developed. And certainly, a lot of cases that we applied here, if you only want to try to understand the alloy impact, then you're actually not necessary to be so worried about, because this one actually eventually can give you a kind of understanding for the tendency change. And it's still quite useful compared with the traditional measurement. So I think we still have a long way to go. And at last, I would like to say high throughput experiments is not necessary just for the validation purposes, not only just for helping the model development, but during the design of the high throughput experiments, we sometimes also can utilize the simulation to guide our design of the high throughput, to pick up the right temperature and the right composition and right time to study this. And I hope with the community develop such kind of high strong interest, eventually we can develop more and more robust high throughput experiments to serve the purpose of additive manufacturing design. Thank you very much for your attention.